All right, guys, this is the lesson from class. I might be biting off more than I can chew, but I'm worried that due to 45 minutes, technical difficulties, attendance, all these things, I just want to make sure that you go to Google Classroom and you see a video of everything we did in class, detail by detail, just in case for whatever reason you get dropped. I don't want you to miss out on that. So I'm making this video. I'm going to try to make videos for every class prior to the class, think of it as a practice session, and then you'll be in class, you'll see the video. I can't always promise you that, so you need to come to class, and really take notes, and then you always can fall back on the video that I post. I might regret this. You guys need to be present. Promise me you'll be present. Okay. All right, so today's lesson is about what's called a rational function. And here's the cool thing. You've dealt with functions for a long time. You've dealt with what are called linear functions. So you've seen functions like this, right? F of x equals 2x plus 3. If you plot points, you see a line, you have the slope and the y-intercept and all that. You spend a lot of time plotting linear functions. Well, a rational function is also a function. The curve fits a certain model, but a rational function is a fraction. Okay? It's a polynomial divided by a polynomial. So every one of these functions here, right, the term rational literally means can be expressed as a fraction. So rational always has something to do with fraction, something that can be expressed as a fraction. And for functions, it means you literally have a polynomial over a polynomial. Okay? And the graphs of rational functions look kind of strange. They look wonky. So if you look at this graph, you can see the two blue portions. The two blue portions are the graph of a rational function. They represent one graph that is a rational function. Okay? Those red lines are called asymptotes. Okay? Asymptotes are lines that a curve approaches but never touches. So if you notice this first portion of the graph, right? You see those arrows. Those portions of the graph actually approach this red line. And then this portion of the graph actually approaches. Now, approaches but never touches is really getting us into some calculus concepts, but this is pre-calculus, so that's okay. All right, so you're going to actually take the time today during this lesson to find what are called asymptotes. They kind of guide the curve. So you will draw a horizontal asymptote, which is a flat line. You'll graph a vertical asymptote so that you can make a sketch of the curve using that as a guide. Okay, so that's what a vertical asymptote is. That's what a horizontal asymptote is, and we're gonna see how to find them and then how to apply that maybe next Tuesday. But today it's how do I even find what that line is? We're going to learn that. Okay, most functions, not all functions, at some point on the graph, and I'll put this in orange, your curve is going to touch, it's going to touch the y-axis. All right, so this curve touches the y-axis at -2, so the y-intercept is -2. Okay, so we'll see step by step how to actually find y-intercepts. Okay, not a bad process. And then we will also see, let's put it in purple, x-intercept. It looks like this curve touches the x-axis at 6, so the x-intercept is 6. So I just want to give you an example of here's what the graph, this is what the end result is going to look like. These are the attributes, the characteristics of the function that we're going to be finding, and I just want you to see what they look like before we actually find them. And then the strangest characteristic of all is what's called a hole in the graph, and you can see this little circle here. There's an actual hole in the graph, meaning you can plug numbers in for x and get numbers out for y, but when you plug in 2 for x, you get what's called an error message in your calculator. You've seen that. You're going to see numerically why that happens sometimes, and we're going to see algebraically how to actually find the hole. That's going to be kind of the longest Not the most difficult to find, but that's a process. So we'll get to that. Okay, so this is what the end result is going to look like when you're done graphing, and these are the 5 characteristics you're going to have to find in order to graph. Characteristic 1, x-intercept. So let's talk about what an x-intercept is as an ordered pair. That purple point is the point 6, 0, which means when x is 6, y is 0. So to find an x-intercept, you need x to be some number and y will always be 0. So let's do an example, okay? So the goal is, if I give you any rational function, how do you find the x-intercept? And here's how you do it. The question is, when will the function, what value for x will make the function equal 0? Well, the only way a fraction can equal 0 is if the numerator equals 0. Okay, so I want you to stop right now and write this. To find the x-intercept, set the numerator, set the numerator equal to 0. Now you see why that skill last week was so important. So to find the x-intercept, you set the numerator equal to 0, and you factor, and I'm going to factor this quickly. You'll spend some time factoring. You're going to get a lot of practice factoring. I need 2 numbers that multiply to negative 50 and add up to negative 5. Those are going to be negative 10 and positive 5. So you solve, set each factor equal to 0. This is why that first assignment was so important. You're going to become an expert. Add 10 to both sides. Subtract 5 from both sides. Okay. We're going to see in the graph in a little bit, to find the x-intercepts, the question is, when will the function equal 0? And the answer is, boop, bow. If we were to graph this function in Desmos right now, and we'll actually do this Tuesday, or we'll do this in our next lesson, you would see that this curve would touch the x-axis twice. It would touch it at negative 5, and it would touch it at 10. So to find the x-intercept, you set the numerator equal to 0 and you solve. Bam. Done. Skirt, skirt, scot. Okay, so we know how to find an x-intercept. Now how do I find a y-intercept? Well, let's talk about what a y-intercept actually looks like. It's a point. Point where your curve touches the y-axis. Okay, so that point is 0, negative 2. Which means the x value will always be 0 at the y-intercept. So to find a y-intercept, you need the x value to be 0. If the x value is 0, you will be on the y-axis. So let me repeat, write this down. To find the y-intercept, you plug in 0 for x. That's it. So to find a y-intercept, so let's do an example. To find the y-intercept, you literally take the function and plug in 0 for x, which means you plug 0 in everywhere there's an x, and you do the arithmetic. Okay? So y-intercepts, I think, easiest one to find, but it's also where a lot of students make basic mistakes, so be very careful. 3 times 0 is 0, plus 21 is 21. 0 minus 2 is not 2, it is negative 2, and 21 divided by negative 2 is negative 10.5. Okay? So, and here's the beauty of a function. I know you remember this, but a function, right, has to pass the vertical line test. What? I know you remember that from middle school. It's been a long time. When you draw a curve, right, what I'm drawing right now is a function. But if the function goes to the right and then comes back, I say the function. If a graph does that, it's not a function. So if a function has a y-intercept, it can only have one y-intercept. The curve, if it's always moving to the right, can only go through the y-axis one time. So the y-intercept is either going to exist one time or it's not going to exist. So all that to say, to find the y-intercept, you plug in 0. Sometimes the y-intercept does not exist. We're going to see an example of that. If it does exist, there's only 1. Okay, we'll do more with that. So to find the x-intercept, to find the y-intercept, let's see what's next. Doot, doot, doot. All right, so now, how do I find vertical asymptotes? And vertical asymptotes and holes go together. So I will say this, and then we'll do an example. Vertical asymptote, hole, is what's called an excluded value. Happens where there's an excluded value, okay? And an excluded value is any x value that makes the denominator equal 0, right? You know you cannot divide by 0. If you put 5 divided by 0 in your calculator, you're going to get an error message, or you're going to be told that that value is undefined, UND, right? So when you have rational functions, anytime you have fractions, you run the risk of, when you involve algebra, of the denominator equaling 0, which is a, bells and whistles go off. That's no good. You cannot divide by 0. So you're going to be given a function, and the question is, when does the denominator equal 0? Because if the denominator equals 0, bad stuff happens. And that bad stuff is called vertical asymptote or a hole, and we'll see what that is. Okay, so to determine if there are vertical asymptotes or holes and they kind of work together, you have to factor everything. So I'm going to factor, so to find these, you have to factor the numerator, which I'm going to do quickly, x times x, right, because we have x squared. X times x is going to give me x squared. So I need 2 numbers that will multiply to negative 20 and add up to 8. That's going to give me positive 10 and negative 2. Now you're going to have to take that off to the side and do some work, which is why when we actually have a quiz over this stuff, you're not going to have but 1 or 2 of these total. So you're going to have to be able to take your time and factor and do it correctly. Okay, now I need to factor this trinomial. Now this trinomial has a greatest common factor, okay? So we have a 3, we have a 9, and we have a negative 210. They are all divisible by 3, so the first thing I'm going to do is factor out that 3 and then divide every single one of those terms, okay? So you divide all 3 by 3 and you get this, but this trinomial can now be factored. So once again, I'm playing that same game. I need to find 2 numbers. All right. So the numerator, x plus 10, x minus 2, but we need to factor this trinomial. Okay, so I need 2 numbers that multiply to negative 70. Now, the first thing I think of when I think of multiplies to 70, this is where that number sense comes in, 10 and 7, but they have to add up to positive 3, so the larger one must be positive, the smaller one must be negative. Okay, so here's what I need you to know. The denominator cannot be 0. Okay? So here's what you're going to do. You set each of the factors in the denominator equal to 0, and you solve. So x equals negative 10, x equals 7. Okay, one of those, both of those might be a vertical asymptote, whatever that means. Both of those might be a hole, but any number, right, that makes the denominator equal 0 is going to have something to do with a vertical asymptote, something to do with a hole. Here's how you make the distinction, okay? A hole will always result when you have common factors in the numerator and denominator. So because you have an x plus 10 and another x plus 10 and they divide out, that means that you will have a hole where x equals negative 10, Okay? You catch all that? So I know there's going to be a point that has been plucked out or pulled out of the curve of my function when x, in this case, is negative 10. Okay, we'll do something with that in a minute. Okay, so anytime there's a common factor in the numerator and the denominator, bloop, you have found a hole in the graph. We're going to do more graphing with that in our next lesson. Today we're just finding it. If you have a factor in the denominator that is not in the numerator, then that is going to be that line x equals 7 is going to be a vertical asymptote. Okay, so I just want to remind you, anytime you see x equals a number, that is going to be a vertical line, and that vertical line is going to be a line that the graph gets close to but does not touch. Okay? And we're going to graph all this later. We're just finding it now. So every factor in the denominator is going to give you a hole or a vertical asymptote. Okay? All right, so let's finish up this whole example. And you've almost seen everything. Okay, and then it's just a matter of practicing. Okay, so let me pull that problem. Let me capture that real quick so we can pull it into the next slide. Okay. Oh my goodness. Okay. You know what? I'm just going to write it down. Technical difficulties, that's okay. I'm learning a lot in the last few months. All right, 10, negative 2, 10, negative 7. Got it. 10, negative 2, 10, negative 7, and there was the 3. Bow. Okay, so this was my original function in factored form. Okay, we divided out the x plus 10. Okay, so we're left with x minus 2 and, okay, let me make sure that's correct. 10, negative 2, 10, negative 7. Yes. Okay, so here's what you do. To find the hole, we can't plug negative 10 into the original function because the whole point of this was if you plug negative 10 into the original function, you're going to get an error message in your calculator. Any number that makes the denominator equal to 0 is going to give you an error message. So the nice thing about this is to find the hole, you take the simplified version of your function. Okay, we're going to see why simplified. My wife laughs at me. I cannot multitask. Simplified version. So, and this is really getting into the calculus, which is what you're going to do month 1 in your calculus class next year. But for now, I'm just going to say this. This function, original, and the one where you actually reduce some, canceled out some of the factors. Those two functions are identical, except for this one point we're about to find. One includes the point, this one, and one does not include the point. Remember, we're talking about the original function having an actual hole in it, meaning a point that's been pulled out. So to find the hole, you find the factors that they have in common, right? X plus 10, x plus 10. You set it equal to 0 and solve. That's the x value of your hole. Then you have to take the x value of your hole, which in this case was negative 10, and plug that number into the simplified version, which is going to be negative 10 minus 2 over 3 times negative 10 minus 7. So this is the one process that's a little bit longer than the others. Negative 10 minus 7 is negative 17. Negative 17 times 3 is negative 51. And then Desmos will actually reduce that for you, and that's going to reduce to 4 over 17. So the whole final answer is the negative 10, comma, the negative 10 plugged in gave me 4 over 17. Okay, and we're going to see this when we graph it. If I were to graph this original function and zoom in on this point, it would literally be missing. You would have this nice smooth curve, nice smooth curve, nice smooth curve. Bloop, there'd be a point missing. You'd see a little circle. And that point would actually be the point negative 10, 4 over 17. Okay, so that is what a hole is, and that's how you find it. Okay, so let's moving on a little. Last but not least. Okay, so finding vertical asymptotes, finding holes, lots of factoring, but you'll practice, which is what Delta Math is going to help you go through that process multiple times until you feel good about it. Horizontal asymptotes are a lot different, meaning to find vertical asymptotes, it's all about the denominator. Horizontal asymptotes, are all about the degree of the numerator and the degree of the denominator. So there's really 3 cases. Okay, so here's the first case. The first case is if the degree of the numerator is greater than the degree of the denominator. Meaning, if the largest exponent in the numerator is 2, and the largest exponent in the numerator is understood to be 1, if the degree of the numerator is larger, which it is in this first example, there is no horizontal asymptote. Now remember, we're finding all this stuff before we actually graph it. Okay, so we got to find it, then we can graph it later. So if the exponent in the numerator is larger, done. You just say on the quiz or on the test, horizontal asymptote, none. There is none. Okay? Let me move my head out of the way. If the degree in the denominator, let me tweak that. I need to remember to change that. If the degree in the denominator is greater, okay? So you have the degree on top is larger, done. There is no horizontal asymptote. If the degree of the denominator, in this case 2, is greater, then the horizontal asymptote will always be y equals 0. Okay? It's a flat line where y is 0. It's actually the x-axis. So that happens a good bit of the time. Okay? It's this other case that's a little weird. So let me draw this one in orange. This one's strange. When the degrees are the same, so in this case you have a linear function, x to the first power, the degree is 1, and you have 2x understood also to the first power. When the exponents, right, when the degrees of the numerator and the denominator are the same, all you have to do is take the leading coefficient. So the leading coefficient on top is 1, the leading coefficient in the denominator is 2, and the line will be y equals coefficient over coefficient. You literally build the numerical value, and that's the line y equals 1/2. Now, once again, why? That is actually something you're going to study in calculus. Why would those coefficients matter, and why does it matter when the degrees are the same? It's actually a really cool calculus problem, but you will do that next year. Okay, so horizontal asymptotes either do not exist, larger degree on top, exists as y equals 0 when the degree on the bottom is larger, and when the degrees are the same, you build the line by writing y equals coefficient over coefficient. Bam, those are horizontal asymptotes. Okay? Now, let's see. That's really all you need for now. Okay, 24-minute video. I'm pretty sure I can get through all of this in class tomorrow, but just in case I was not able to get through this in class, I wanted to make sure that you had a video where you could see everything, just in case you kind of miss something in class, just in case I get cut off, etc., like we talked about. So we will actually do these last couple slides at our next session. Okay? So no worries. Alrighty, that's it for now. Keep studying hard, keep working, get into Delta Math, and do everything up to the actual graphing part. You need to be an expert at finding x-intercepts, y-intercepts, vertical asymptotes, horizontal asymptotes, and holes if they exist. Next time I see you, be safe.